Okay.
Okay, I was midway through the ACLID extinction backscatter depolarization ratio algorithm. So that's a high resolution optimal estimation procedure for getting the extinction and the backscatter and the depol ratio for all the targets, the water and the clouds, or the strong features and the weak features. So, and this is coupled both the A-EBD and A-AER, so the first pass and the optimal estimation second pass both use the same subroutines for the target classification procedure, which operates on layers. And it's not a, you could use some type of neural net for this, but this is more of a traditional decision tree. So when you go through the code, there's a lot of if statements depending on the temperature and thresholds in the backscatter to extincted ratios, and so on. And we know that this is one of the first things we have to tune a bit better based on real data, because I think I already mentioned that that problem we've already noticed in preliminary data that for optically thick aerosol plumes, we're sometimes calling them clouds when they're clearly not. So, but we think we can fix that pretty easily for the vast majority of the cases. So you can prepare for quite a long time on simulated data, but of course there will be surprises when you have the real stuff. That's, but you've got to anticipate that. So I'll just get into the, unfortunately, things are still under not released yet, so I can't show much in the way of real data yet, though I will show some teasers later on. So most of what I'll have to say here is still based on the old simulations. So I should let this person in again. Oh yeah, that's you. Okay.
Yeah. But you see it here now.
No.
But I also have it here.
Okay. Anyway, so this is an example based again on this Halifax scene. Here's the model truth extinction, the simulated particulate backscatter, and we simulated molecular backscatter. And I'm happy to say, when the paper comes out, that if I ever have time for it, sort of evaluating how good the simulations were in terms of representativity of the instrument performance based on the real data. I think we did a pretty good job. It turns out the simulations are certainly within the right ballpark when it comes to the sensitivity and everything. So we're happy with that. So anyway, good. So we can simulate the level 1 observations, and again, this is a kind of retrieval, so it's a different version than what I showed the 6 or 7 year old presentation earlier. So the aerosol is somewhat different, but the key point remains that we're able to distinguish the different types of aerosol here, based mainly in this case in the extinction to backscatter ratio, because neither of these layers is very depolarizing. I don't know if you can quite see it too, but then if you look at the retrieved extinction ratios, the backscatter extinction ratios, you can begin to see the fact that it's in layers. So it's been smoothed somewhat because this is a low resolution product, but you can still fundamentally see the layers back in it. Next. Oh, okay. It seems to change all the time. What's the keys I have to press? But anyway, and again, this shows more of the same data, but it shows how all this gets translated ultimately down into the target classification, in which you can see that this is correctly assigned as a different type of aerosol, the continental pollution over the marine, and you can see then that the cumulus clouds are there. to correctly identify. And it still remains a problem, even at the simulated level, having strategies in which you would avoid the cloud signal bleeding into the aerosol signal bias things. Was an issue in the simulations. I'm sure it'll be an issue in the observations too. So it would be good from the let's say the Cal-Val point of view of having some circumstances indeed where there is clouds, some clouds, right? Not too many. Then you don't get any good aerosols, but some, let's say, more non-ideal conditions where you have aerosols between scattered clouds would also be nice, interesting for us to. And this is some statistics, some information about the not statistics, but some information about the differences between the different products, especially the A-AER products and the A-EBD. Because of the smoothing, the extinction retrievals for A-AER are usually there's some horizontal smoothing going on too. So they are lower resolution in that way. And lower resolution in the horizontal, and the A-EBD, even though the true, let's say, representativity, especially of some of the a prioris, is variable, and that feeds back into the real resolution of the products. Basically, at least the grids range from 1 kilometer for the strong targets, and the medium and low resolution are typically like 50 and 150 kilometers. And that is reflected in the target classifications too, which are provided at the different resolutions. So they are consistent. And again, for the ice products. So if you compare some of the A-ER retrievals of extinction and LiDAR ratio, this is LiDAR ratio and top extinction at the bottom. You can see at least when you plot things on a large scale, there are differences, and usually you want to use the A-EBD products. There's been a few more checks in there that aren't present at the A-AER level. Even though the data can be sometimes a little bit noisier than the A-AER, it's usually, let's say, maybe a little bit more precise but more accurate. So, but depending on your application, either could be suitable. But I would lean towards, when you do the comparisons, to use the A-EBD products and the low resolution for the aerosols. And again, with the target classifications, you can see those differences between the different versions. So you might think of this as being a little bit redundant. But also it gives the user and us as developers some confidence in how robust things are too. So if you see a feature coming and going depending on the resolution, you might think, oh, maybe that's not a real feature but an artifact of some kind. But if you see it present in all the resolutions, then it's probably a real feature. And even with A-EBD, you can see the difference between the high resolution products on the top, that's at 1 kilometer, and you can see the aerosol is markedly, it's noisier there. And the medium and low resolution is different less, but still you can see this is generally smoother. And you can also see that the smoothness depends in the aerosol. There's a big difference between the low resolution and the GSD resolution, the high resolution. That's visible on these plots. But with the strong features, you can see they're largely the same for all resolutions. So that's reflection of the fact that you're trying not to smooth over the files.
What is the Jordan's volume in the third plot?
Which? The vertical. This is connected with this arrow to this extract. So here's a profile, and I can't remember originally why I put this in, but this is, okay. So this is a profile for there. So you have the really attenuated backscatter, the particulate attenuated backscatter, and the red lines here are actually there's not a red line, there's a solid dark line here and a red line there, I think. It's not showing up too good. But I mentioned this is a A-EBD, this is an optimal estimation forward modeling approach. So this is the predicted LiDAR signal when the thing is converged. So this is just demonstrating that it's the forward model in this case is providing a good fit to the observations. And then along with those observations, along with these fits, this is the retrieved state vector, at least the extinction part of it. And you can see that that extinction is at 100-meter vertical resolution. But the associated extinction to backscatter ratios, or the S, is you can see here the blockiness, and that's due to because that's in layers. So again, the extinction is always at 100-meter resolution, or 500 meters above 20 kilometers. That's where we change resolutions in the level 1, and then the S is reported is modeled as being constant within the layers. What I didn't want to see on this. Okay, and so this is of course pre-flight data. So we've done a lot of work to see how accurate and what the precision is that we can expect based on the simulations. But here, this is that same scene, and this is an extract of the profile average around 10 kilometers of the retrievals and the model truth. So simulations are only simulations, and you try to do your best in reality, but they have one advantage compared to the, let's say, the real atmosphere, is that you know what the truth should be. So, and it was a very invaluable process to have the retrieval algorithms to be able to develop them in this environment, because at very minimum, it was very helpful in tracking down bugs in the code that you would never, ever would have noticed comparing with real data because of the associated uncertainties. But this also demonstrates that even when you know what the answer should be, that it can be if you do very advanced simulations, and then even at the retrieval stage, you're not able to model everything that went in the simulations, such as being able to having to deal with realistic signal to noise ratios and inhomogeneity present even in your test data, that you can't expect to get exactly out what you put in. Only in very idealized situations would you turn the simulation noise off, then you turn off, and you make then you have scenes which are vertically homogeneous. So we get a good feel of what we can expect and not expect for the algorithm performance. And so we're still within specs, but we can see that we assign honest error bars in this case for the high resolution products. There's still a fair bit of uncertainty, and that's because the signal to noise ratio of space-based LiDAR will always be below, and it will be a constant, and that will be true at least for the next few generations of space-based LiDARs that may or may not come. So here's just retrieving the associated the extinction. The blue is the model truth, and you can see the limitations down here. You can see where the associated error bars estimates of the algorithm are good. For moderate extinctions, too much extinction, you lose signal. Right down here, but in the areas where we should be sensitive, we're doing quite good. Of course, up here it's very tenuous, so these are logarithmic scales, and we're going down to fairly small extinctions. And here the LiDAR is, it's being attenuated, and there's not so much ice. And you can see the correlations here, and this is in the aerosol. So when we get a snapshot, there can be, depending on the level of the extinctions, you can expect several tens of % disagreement with, let's say, a ground-based observation in the best case. And if you can do that for the extinction, you can also do that for the extinction to backscatter ratio, which does not vary as much. But you can see here that in a lot of cases we will, yeah, we can get, it's fair to say that we're sensitive in the large changes in the extinction to backscatter ratio, let's say on the order of 10 or so, but smaller changes, not. So the sensitivity is not quite there. And part of that is the limitations in both the retrieval methods and some uncertainty due to multiple scattering. And yeah, the third factor is the variability itself. And one particular area of attention has to do with, now pointed out here with the cursor, you have the biggest errors in the extinction to backscatter ratio measurements are actually under this bit of cirrus cloud here. So this cirrus cloud is enough that there's it's thin enough that the LiDAR penetrates it well, but there's some multiple scattering effects that actually propagate down into the retrievals of the aerosol below that are hard to model. There's a procedure in which we try to account for this, but it's a tricky thing to get it completely right. So that will be another area of interest in how we're doing getting retrievals under thin cirrus. Because there's a lot of places in the Earth where there is a lot of thin cirrus and will penetrate it regularly, but underneath, at least for depending on how thick that cirrus is and what the particle size is, that's an important parameter to that for the multiple scattering, how much that will affect the retrievals underneath.
But wouldn't you expect also that the polarization ratio to be?
No, the depolarization ratio isn't so affected as much as the
Extinction.
yeah, because it's mainly forward scattering. So and that remains unpolarized as you go through the cirrus.
Yeah, no, I mean, but here below there.
Here, that's just a bit of, it's still noisy. Yeah, I mean, like I said before, in this simulation anyway, the depolarization ratio of that aerosol is pretty low. There's very little dust present, for example. So it's below a couple percent.
The polarization ratio is the particle, right? Not the
Yes. No, not for the volume. Well, that's another thing we should have mentioned at the beginning. The level 1 processor is designed so that the particulate depolarization ratio is reported. So the removal of the Rayleigh component is done at level 1. And that will be another very interesting thing to verify with the ground-based measurements. We know we're doing pretty good with the depolarization ratio in the high depolarizing targets, but no one's really looked yet at how good the real data is going to be when we have low depolarizing aerosol.
So level 1, the polarization ratio is provided, but it's the volume 1.
Instead of the volume 1, no. It's different because the volume 1 is very, well, it depends a lot on yeah, we can't really do what a conventional LiDAR does there because of the way because the Rayleigh channel has a different spectral footprint than the depolarization channel. So it would be, yeah, and if you want to recreate it, you can. But when you want to compare, if you want to compare our depolarization ratio with a ground-based measurement, you have to derive the particulate depolarization ratio. Otherwise, it's going to be way off.
Yes.
Yeah. And we've also looked at other scenes different from the Halifax scene. So this is another one of our training data sets. And this is our so-called Baja scene because it actually starts, well, way up in the Canadian Arctic and crosses the North American continent, across the Rockies, the Sahara Nevadas, and exits across the Baja Peninsula of California. So this one is different. You can see a lot of aerosol up there, clouds, and the Rocky Mountains. So there's a lot of topography there. And that's also something that needs to be handled with the algorithms, because of course you don't want to. It's no good if you start including surface returns in your when you start to analyze your LiDAR data. And this is a simulation, and this is a simulation of what 4 channels from the multispectral imager would see in that scene. And you largely see things similar to what we saw in the athletes in the Halifax simulation, sort of similar order magnitudes and of correlations and let's say robustness of the retrievals. And again, it's yeah, the true extinction to backscatter ratio when the retrieved one, not perfect. And we were talking about color scales earlier, so this actually comparison is worse than it looks worse than it really is, because actually the difference between yellow here and red is less than 10%. But you can see that even in the let's say the simulations, even when we know what the answer should be, then it's the retrievals are not perfect. But we have a pretty good idea of how good they should be. So getting on to some more of the, now this is probably a little bit old too. I think things have improved a little bit, but we have been very conscious from the start about trying to come up with useful quality status variables, which when you use the data, you should pay at least some attention to. For every one of the products, there's usually 2 levels of flagging. Not every Earth Care product has this, but a lot of them do. There's sort of common quality status. So for every Earth Care data product you open, you should see at least a minimum of quality status flag, which ranges from, so it's very simplified. It's somewhat qualitative, but 0 is good. That means the algorithm developer is happy. 1, there might be some small issues, but likely good. And that ranges from likely bad to pretty too bad, so pretty much unusable. And 4 is just missing. There was no level 1 data to process. Then for every algorithm, then all the developers have the freedom to add more information if they want it. And for A-Pro, it's some of the, for A-EBD, you'll see many more flags. And some of this is more, let's say, for the algorithm developer than the end user, but still would be useful. So, you know, special cases in which the optimal estimation routine did not converge for some reason. So that points to probably some undiagnosed error. When the maximum number of layers was reached. So for reasons of performance, we try to limit the number of layers the atmosphere, horizontal layers the atmosphere is divided into. And if the code still wants to make 20 layers when you think the limit should be 15, then that's a sign probably something that's going wrong too. And various others. There's also, for each channel, there's a detection status. So ranging from the me on the particular channel, if there's -3 is missing data, -2 is that's the surface or below the surface. -1 is where we estimate that there's no usable signal because of attenuation above. 0, a very important one, that's where we judge that it's pretty much can be considered clear sky, and 1 if there's an aerosol or cloud target present, and something similar for the radio channel. And some other points of attention we're using the data is that, of course, we already covered this, that the data is reported on the joint standard grid, but depending on what variable you look at, the real representative resolution can be different. Yeah, there's multiple scattering is modeled, and we'll talk about that's a whole other talk about that. And there'll be and some of my particular concerns about, are going to be how well are we doing in cirrus, in which multiple scattering is going to be a problem, needs to be handled all the time. And in some cases, when we have dust and sea salt, when the particle size gets bigger, I expect some multiple scattering influence there. So any ground-based measurements in those kind of conditions will be especially valuable. And for when people get enough, let's say, experience with the data themselves, they may not be satisfied with our simple, high, medium, and resolution-based approach, and they want to do their own smoothing sampling. And I say, go ahead, but don't do it blindly. Pay attention to the following flags and be smart about it. Otherwise, you can and will get some strange results. So I can't present too much in the way of Earth care, but I can say a few words about what we did with real data with Calypso. And so some of these algorithms, so we had AFM and APRO, and they gave rise to AEL-FM and AEL-PRO, which were adapted to Aladdin measurements, and that's the recently deorbited. Well, when did it come down? It's not recent anymore.
2023.
Yeah. So yeah.
Yeah.
So it's no longer up there. And it's a shame. It did a stellar job, but it was a problematic thing, and very much it never really got out of the commissioning phase because things were changing all the time. Even a bit by design. For example, the range gate structure was changing all the time deliberately.
Yeah, all the tests. For all the, for all the tests, etc. And they were doing all these things to test different options in order to know better for the next missions. So all these things were easy.
And not only, let's say, for that reason, but operationally, it was always changing with latitude bin, and when the tongue went off, of course, it would switch higher. So always fiddling. So, and it was never optimized for aerosol observations or cloud observations, but we managed to get something out of it nonetheless. So I've covered, you've seen this before, so this is how I've managed to adapt. Not in some parts we were not able to use the same codes. We can't do that, but we were able to adapt a lot and test a lot of the ideas, specifically about the separation of low and high resolution, strong features and weak features, and how well trying to separate the aerosol and cloud was. It was trickier because, of course, the resolution, not only in variable, was a lot cruder than applet, and the signal-to-noise ratio was much less than applet in a lot of cases. So, but we were able to do unlike Earth care, Aladdin was orbiting at the same time as Calypso. So we were able to do things like find coincident tracks, in which case, as an example up here from the Calypso quick looks, you could see here you have a very nice circumstance where you have a nice homogeneous aerosol plume. So this is what Calypso saw, and this is from the me channel after correction for crosstalk, which is a whole story in itself, how you do that nicely with Aladdin. And we're seeing the same thing there. We're seeing the same thing there. And that is, we're certainly seeing the aerosols in the same place. So Ping Wong at KNMI did a lot of comparisons, which is out in a paper now, recently released in A-EBD, comparing things like the AEL-FM, which is the Aladdin counterpart of AFM, with the Calypso vertical feature maps, and at least on the qualitative level, not bad. And even if you, like again, pick the right targets in homogeneous aerosol fields, you can even get reasonable comparisons on the of extinction retrievals on the profile scale. Of course, a lot of you have to overlook some things. For example, this peak here is not real. That's due to a missed hot pixel, which if anyone had anything to do with Aeolus knew that the pixels were a real pain to deal with. So these are pixels, and it uses CCD detectors. And these are wonderful devices, but one weakness they have is they can be damaged by radiation. And when that happens, the dark count rate of that pixel can go up. And then that dark count rate has to be properly removed. But the problem is sometimes that dark count rate after the pixels become hot will change spontaneously and randomly. So, and it becomes almost a incredible bookkeeping exercise to keep track of the dark count, the current dark count maps, and remove these pixels. A lot of manual work. So I'm sure that and DLR have put a lot of effort into that.
So once the dark pixel, not for Aeolus, I remember that they were trying to find him. For A-AER, there is already one dark pixel, right?
More than that.
And,
So it's going to be a real pain in the ass.
and then in this dark pixel, once it is observed, the decision is to totally exclude it, or it is to try to
No, you
regulate
can't
it
totally
every time.
exclude them, but you can do things. You can measure what the dark count rate of those pixels of the whole array is, just by taking measurements with a laser off.
Ah, okay. So you can recalibrate it very
Yes,
separately.
so you acquire what's called a dark count map.
Okay, I see.
And that then can be used to go forward to reduce the right amount of.
No.
That's the big question. How often depends on how often these dark count we need to do it. But it's envisioned more like weekly now. But you can never tell. You can only sort of tell after the fact, because you can take the instrument offline for a while, get a good dark count map, and then God forbid 2 hours later, then a new hot pixel appears. So you never know about the gaps between the dark count measurements, except to say that we're building in detection routines into the level 1 processor to detect new hot pixels and to optionally do a correction to sort of bridge the gaps between the measurements.
Okay, when do you think this routine will be able to be?
It won't be active in the data that you'll get very soon. So you will notice a couple of pixels, but in the next iteration of the processor, it will be, and it should be implemented before the before the end of the commissioning period.
So in
So at the end of the year, basically.
okay, that's good enough.
Yeah. Okay, and if you can do this for, let's say, one retrieval, you can, yeah, it's noisy, it's a logarithmic plot, but it shows that Calypso and on average, and Aladdin on average, we're doing very good in dust in terms of the correlation between the data. So it's, Ping was very, let's say, generous in the color plots, but if you look at the density, you should really just focus on the green, on the intense colors down here. And we're quite happy with this because there's like a 1,000 things that could go wrong that would prevent you from getting a good correlation. It also shows that Calypso, at least for dust, is assigning good extinction to backscatter ratios, and they're handling any multiple scattering in the dust quite well.
Just a second, circling back to hot pixels, are there any takeaways from years that you implemented into EarthCare?
Yes, one of them was the fact that we would have to think about Airbus were saying, and they're more or less, well, they were saying that we wouldn't have to worry about them at all. Probably. But it turns out that, yes, we do have to worry about them. They're not as intense as Calypso. as Aeolus. They don't appear to be as, it's still early days, but they don't appear to be appearing as frequently.
Because the reverse it went bigger.
Yeah, they start, yeah.
Mm.
And we seem to have more back in August, and now there hasn't been any one for a while. But all this is very preliminary, very extremely preliminary. We only have a short record. But we also know that from the popular news articles, there was some solar magnetic events.
Yeah, I mean,
that-
the solar activity is still rising.
Yeah.
We expect more.
So,
Wow.
yeah, but they are different devices. But we have noticed the occurrence hasn't been constant, even within the short lifetime of athlete. So hopefully, so we hope for the best. Few new ones, but we are prepared for if it goes bad. So-
Yes, because now you have higher solar activity in comparison with the other time. And
But I'm not an expert on solid state physics when it comes to CCDs and radiation damage, nor am I an expert in any space weather things, or the coupling between solar activity and what really goes on at with this. Most of the problems are associated with this so-called South Atlantic anomaly.
Yeah.
And how that's coupled with the proton or anti-proton density there, whatnot, how that's coupled with solar activity and what the timelines are, I have no idea. But I just know when we have, because we also have speckle noise, we can see where the radiation has hit the CCDs, and every so often, then it seems to damage the CCDs. But we know enough now that there's, it's South Atlantic anomaly that gives us the most problems. But
Yeah, that makes sense.
how that evolves, I have no idea. So, and we were all able to do, this isn't the animation, but we were also able to, it's a bit of a shame now that, okay, everyone's moving to Earth care, but there's still valuable aerosol information in the lab, and that should not be left. And so, before it ran out of time, we were doing things like playing around with, making some climatologies in a way of different aerosol extinction profiles and extinction to backscatter ratio profiles for different areas. And this is a nice one here off the Atlantic, South Atlantic, off of Africa. You can clearly see the signature of desert dust coming in, and I had an animated version of this that showed how it varied through the seasons, but you can see.
LiDAR ratio 120 at 3 kilometers.
It's because of the emissions and stuff.
Yes. So it's an effective, yeah,
Correct.
it's not corrected for that. So Aeolus didn't have a dipole channel. And it only measures and it uses circular depolarization. So the circular depolarization is at least twice as high as the circular depolarization ratio is twice as high, at least, as the linear depolarization ratio. So, and because you're only measuring in one channel, you lose often more in the highly depolarizing targets, you lose more than half the signal.
Okay.
So when you calculate the extinction to backscatter ratio, because you're missing half the backscatter, the extinction to backscatter ratio is at least twice what you'd expect from a linear system.
But is this because at 3 kilometers you don't have so much dust? Is it because of that, or is it because of the fact that you have very few aerosols at this point because it is in between
It's a
the
great
marine?
actually, for this one here, it's,
At 3 kilometers here.
yeah, that's real.
It
And I'm
is.
convinced it's dust. Because you see the months before that, you see it's,
On the Atlantic, it's for a couple of millimeters.
I know that usually, I mean, when we measure there and
Yeah.
when usually are there, it's at 3 kilometers. Okay, at 3 kilometers, yeah, usually you have dust, yeah.
yeah.
I thought it was lower.
And you can see it, I wish I had that animation there, because you actually see the dust come in and the extinction to backscatter ratio before you see a perturbation in the extinction profile itself.
What?
So left one is
So the left one is extinction.
Mm-hmm.
So when you look at the time series of this, the bulge at 3 kilometers comes in before you start to notice a bulge in the extinction itself.
Yes.
And I just have to mention, you should sort of ignore the stuff up here above this line here, which is the freezing level. And up here, that's usually cirrus clouds that are not being filtered out properly.
Okay, so that's why you have these light directions there, again, because of the depolarization. Again, this is
Yeah,
high
it's hard to, it's quite a challenge with ALS to filter them out properly.
Very interesting, Dave. Well done.
You've seen this before, right?
This specific plot, I don't remember. Maybe it was lost in my
It's prevented erosion.
in Robus.
Yeah, sometime ago.
Very good.
Okay. So this is not ALS, and this is not simulated data, but this is some real earthcare data. So it turns out that one of the reasons the release has been delayed is due to the fact that the processor is not doing a good job removing the background solar radiation, which is throwing off the calibration. And this is like LiDAR 101, and the fix is very simple. There's some configuration parameters related to the sensitivity of different parts of the CCD in which the background is measured, profile is measured. Somebody, it looks like, rounded off a factor. So it's off like about 5%. So it'd be like 10 minutes to fix if you had access to everything, but having to go through the formal procedure takes
Of a satellite mission.
Yes. But the nighttime stuff isn't bad. There's
But this is simulated UCD.
No, this is not
This is
simulated.
the first reality. And what do you see the problem here that is still to be fixed?
In this one, there's little problems, but if you could see it at around 20 kilometers, this is some spurious features. And there's no noise spikes, no radiation noise spikes in this frame, so it's pretty good. But you're showing here the total signal. I think that's total. That's
At level 1, this picture there, it is in the area of the change of the resolution.
yes.
Yeah, let's see.
So there's still needs going on. So you have the Rayleigh, the combined Rayleigh and me, but you also have the retrieved extinction, the retrieved extinction to backscatter ratio from A-Pro, and the feature mask. Again, by eye, looks pretty good. The extinction to backscatter ratios they show some horizontal continuity and are within the range we're expecting.
Okay.
But good, you can make pretty pictures and they don't necessarily reflect reality. But ping has also been some very, very preliminary, again, early net comparisons. And this is a site in the mountains and where I think the site in
Tajikistan, which is
Yeah.
this dust.
Except in this case, it doesn't look like it was dust, but anyway. So there's the profile, then through the products, the classification, and when you actually compare with the retrieved extinctions. So there's cirrus cloud above, so none of this can be really expected to compare well. But in the aerosol part, we're doing seem to do. Granted, it seems a lot of plots you can hide along there, but I was very happy to see that they were on there. You could plot them on the same axes.
Yeah.
So when we have already a scattered amount of comparisons. And I was very happy to see this because we know there's some issues at level 1 that have to be fixed, so it should only be better. And we do have some more examples to show that this is not a one-off. And we already know there's some things need to be fixed, but
Below 1 kilometer, you don't show it because you anyway expect to have a discrepancy.
well, before 1 kilometer, you're underground there because it's an elevated site.
So you have so good up to the ground. So you have so good comparison between the extinction up to the ground. Okay.
Yeah, that's. I mean, there will be an overlap area for the overlap of
The system.
Yeah, we won't get any. I mean, there's always first 100 kilometers will be suspect.
Yeah, because on the simulator that Peristera ran these cases, it seemed like in the first kilometers there were still things to be improved.
Yeah,
But here it's not that different.
yeah, but it's a bit upscale here. To be honest, I don't know if Ping plotted the first, if this altitude is above the altitude from sea level or no, because that site is already,
Because
it's already 2 or 3 kilometers high, so this must be above
above the system.
yeah. No, it can't be. Probably not above the system.
How far is the overpass from the site, the ground site?
No, that would be good information to be included in the header, maybe.
Yeah.
Because I gave you the.
I can't remember what the window Ping used here, but I think it's a few kilometers at least.
Few, not
Not hundreds, no.
thousands.
No.
Just a few kilometers, like 5 kilometers, 10. Okay, very good overpass.
In this case, but I'll emphasize here, this is not to be distributed and it's still extremely preliminary.
Yes, and the Tajikistan station has big mountains next to it.
Yeah.
Very interesting.
So, along with the level 1 release has been delayed, but the level 2 processing chain is up and running with issues, but I expect that it will be still useful for the CalVal teams to have access to that data, so they should get that relatively soon after the level 1 is being released to the CalVal teams. Of course, that decision is not up to me and ultimately up to ESA. And I would say that and I will mention that that rather formidable looking, incredibly complex processing chain, we have had that, it is executing regularly to the end. So a lot of products will be available.
When you mean relatively soon, like after January, you imagine, after the level 1 workshop, for example, something like that.
Yes.
For the level 2 to be
Level
released.
2.
Yeah. So maybe they wait until then.
Will be released from the time that healthcare went on the athlete went on normal operation, meaning from early
From
September or late August when athlete start.
Yeah, things are only.
But the release date on. I mean, are we going?
No, there will be.
This period?
Not right away because there will be a reprocessing. As I've been told. Again, I can't speak for ESA, but informally I've been told that there's people, there's obviously demand for the data from the beginning, and that realistic period is something like at least mid-August, when they had the laser tuned.
Yeah.
Because it was running for quite a while. First, they had to do the physical alignment, because unlike AOLIS, Athlete is a bistatic system, so the laser beam had to be brought into the receiver field of view, and then they had to spectrally tune things. So from about mid-August, so it was good. And then they probably could even put that back by a number of weeks, depending on how much effort you need the reprocessing. But that data, yes, will be reprocessed.
But it will become available later, time, not from the date that either will announce, okay,
No.
now level 1 are released, but they will start from the date is on. And the
Peristera, you're asking?
Yeah, there'll be 2 releases. One of them will be from the data from that point on, with the best, let's say the deemed good enough level 1 processing. But then that data, the data from earlier on, it will take a dedicated reprocessing
Okay.
to do.
Peristera is asking because he just returned from a 2-month sleep.
Exactly.
Measuring below
this will
here,
be done for
here.
sure. This will be done for sure. But,
And now seriously, where are the data? I returned, I found the data from the ground, where are
but
the data?
if you guys want the data, even though it's
Now we are in
it's
disk.
compromised, but I'm sure that can be
Arranged. We need to arrange. Also, we are in disk, so
yes.
maybe it's not.
And when the disk
unofficial.
starts up, we have much more flexibility in that respect. So that's it for that presentation.
Any questions? Short questions for the
Audience?
participants? Yeah.
The 20 flags are for each beam or?
Yes. Where appropriate, some of them are only available, let's say, but when the cost function is not, hasn't been, when it's tried to minimize the cost function and doesn't see and fail, then that's appropriate for that one profile. But yeah, most of the flags are for where appropriate are for each altitude.
So this quality status, quality flags, the general.
Yeah, but I think, yeah. Yeah. Well, actually, no, no, I was mistaken there. That even though it only makes sense to be, that particular flag only makes sense to be applied for profile, I think it's just then you'd have a profile exactly the same. It'd be, I think, 4 or something showing non-convergence, but it'll be 4 repeated 2,500 times or whatever. I mean, 250 times or whatever, how many range shades we have. And in addition to the quality flags too, you should also pay attention to the estimated error in the retrievals.
Propagation.
Yeah, because there's circumstances in which you can have very noisy retrievals, but they're still usable in an average sense. So they're not necessarily flagged as bad. They're just noisy. But for your applications, you still might want to filter them out.
Dave, for this, I guess you will, with Ping, you will have some, in the beginning, some global processing and have some suggestion. Because as you said, you have the 5, the 1 kilometer, the 50 kilometer, and the 120. But I guess very soon, if you have a global view, very soon you will be able to say from the signal to noise ratio from the signal.
Yeah.
What is the ideal?
We are at our expectations source, and some of this still will be useful for us for debugging things. So I don't see them being removed from the product. But yeah, at some point, I guess the user community will demand a kind of data user guide or something.
Any questions from the remote participants?
Are there any remote participants left?
Actually, yes, this workshop was not, the way we have this discussion was not so much in the favor of the remote participants.
No. Sorry about that to the remote participants if you're still out there.
But Christian and Nikos are both here, so.
And Julia,
Maria, yeah.
yes, we are still here.
Okay.
But he says, everything is very clear. That's why there's no questions. Now we just need the data, and then we go back with questions to Dave and the forum.
Exactly.
So here at the forum that I mentioned, for anyone who doesn't know, is that ESA has created a forum specifically to post questions about the data when you see them, and asking the developers, etc. And because, for example, not everyone can ask Dave the same. Maybe everyone has the same questions, and they cannot everyone ask the developer straight. They can go through the forum. You post the question there, and then someone replies to you, and there is a whole system behind to support the developers for repetitional questions, to cluster them, somehow reply faster, so that the developers can actually improve the products and not just answering to everyone.
Yeah, no, I would really encourage people to use the forum because, like you said, it was. I don't want to answer the same question 15 times, for example. It can be.
Like in Aeolus.
Like an Aeolus, yes.
It's a lesson learned.
Yeah.
Let's go to the next presentation.
you know,
Then there is the multi-scattering.
yes, so, yeah. So, to in this, see. Okay, and this one is actually going to be a little bit more general and academic, and it covers.
Can I have a question before we go to the scattering? Sorry,
Okay.
because I left and I came back. I have a question. Now, from the community, at this point, for level 1, you ideally, from the community, you would like people to use their data and use the simulator and fastly provide through the forum and through the portal the comparisons immediately after the return. Is there some specific some specific afterwards for the level 2? Are there some specific cases that you expect people to focus more? That you would like people to focus more? Because we will have several measurements, but maybe
If you have to prioritize.
Yeah.
And I tried to say a couple throughout the talk. One of them that's connected with multiple scattering is, I know you guys are more interested in aerosols, but how we're doing in cirrus clouds is extremely interesting. How we're going to be doing with aerosol retrievals under clouds is extremely interesting. For benchmarking, it would be nice to get, let's say, nice cases where the aerosol is nice and homogeneous, where there's no clouds around. But it will be also nice to have observations to see how we're doing when you have inhomogeneous conditions, when you have, let's say, your boundary layer and you've got some clouds there, but there's also aerosols around. If we want to know that we're getting good aerosols in the vicinity of the clouds, and we're not, the cloud returns are not bleeding into what we think are the aerosol areas.
Okay. Noted.
So yeah, if I can give some guidance to the Cal teams, that would be, yeah.
Of course, at first everyone should start with a good case that everything matches, so that we give support to the people, and then
start with easy stuff, gain experience, and then move to the more challenging ones. But
and then present the second slide.
yeah. Okay.
Can we do a summary of what we can compare with the ground LiDAR? For example, you said for the dipole, only the particle depolarization we can compare.
Yeah.
And the products we are most interested is the A-EBD.
EBD. You should. I mean, okay, I hope people look at all of them and make up their own minds what the differences are. But my recommendation is to use the A-EBD low resolution for the aerosols.
Okay.
That's what we expect to be the most, let's say, not necessarily the most precise, but the most accurate.
Low resolution.
Yes, the low resolution products. So.
But everyone should also evaluate the target classification as well from the ground, especially the actress people that will have the multispectral.
Yeah. And of course the obvious stuff, the extinction to backscatter ratio, the extinction itself, the backscatter itself. And anytime there's any kind of in situ, that really tells you what type of aerosol is there. That's very nice too.
Very good. Actually, Franco was asking, Marenko was asking.
Yeah, I don't know how to answer him that. I don't know how to you would directly get the size distributions into the simulation process. You could do it, but it would be an offline activity.
Another question he had was if in the simulator there is it has the possibility to use systems of 355, another wavelength, 355 552. Yeah, if it's
Yes, yeah, for sure, but you'll have to do you would have to do the it's set up that you could do the simulate, say, what things would look like at 5:30. But it's not set up to do, there is options to input, let's say, the extinction and scale it by a certain amount. So the user would be responsible for that part, so they could figure out if they knew what type of aerosol they're dealing with, they'd know what kind of angstrom exponent would be useful, and that they could put in. So it's not in there explicitly, but let's say the flexibility to do that kind of thing is there.
Okay.
But it's not going to automatically.
Yes, you don't select an option.
No, it's not like you said. You can put this. You can put an aerosol profile in and say, oh, this was measured at 642 nanometers. And,
Yeah.
So tell me what it's going to be at
35.
It won't automatically do that for you, and I can't see it ever doing that. So.
Okay, thank you very much. Now, I let
okay.
you start in the next interview.
Under multiple scattering, which, okay.
Δεν ξέρω, πού να κλείσει η εξάρτητη.
New recording? Okay, I'll wait till this is set up.
Μαρία,